Hi, everybody. Welcome. We'll be quickly bringing up our speakers. We're really glad to be here to do this presentation today. So I wanted to thank you all for joining. This is really exciting to see this new platform for having virtual meetings. Really want to thank Heather Benway for her foresight and pulling us together in this virtual way. So this meeting today, I know that a number of you have participated in other activities around ocean carbon certified reference materials. This particular event today was initiated through the Ocean Acidification Interagency Working Group, which I chair, as part of a long-term effort to figure out the long-term sustainability of ocean carbon reference materials. You'll have the opportunity to continue this conversation over the Ocean Acidification Information Exchange, and if you're not a member, you need to be. You'll be, very shortly, there'll be a link showing up, which will enable you to do that, and we'll remind you again about that at the end. So my name is Libby Jewett. I'm director of the NOAA Ocean Acidification and also chair of the Ocean Acidification Interagency Working Group. I'm not going to be saying much other than to introduce a few folks, but we will be hearing from Andrew Dickson from the Scripps Institution of Oceanography, and he'll be giving a high-level overview of CRM production to date. And then we will be hearing from about the NIST Traceable Reference Material Gas Standard Program from one of our co-IWG members, Regina Easley from NIST. And then Shallin will round it out with an overview. Shallin Busch, who's NOAA Northwest Fisheries Science Center, will be providing an overview of other options for the future and changes to the current approach from the IWG ocean acidification perspective. So I'm here from the OAP, but I'm helping co-lead this with Hedy Edmonds from the National Science Foundation, and also Regina from NIST, and Shallin used to be our staff person for the OA IWG, and so she's continuing to be very much in the mix in terms of figuring out our next steps. And so for now, each of the speakers will actually be handing off to each other, and I am going to hand off to Hedy. Thank you.
Thanks, Libby, and thanks everybody else on the panel and in the room for being here. So the NSF Chemical Oceanography program is happy to have been able to support Andrew Dickson's work in this area for the last 30 years. We're grateful to Andrew for providing this tremendous service to the community, and also for the considerable effort that's gone into writing proposals every 3 years to NSF Chemical Oceanography that have consistently cleared the bar for a positive funding recommendation. And a lot of people have recognized for a long time that this is not a model that can be sustained indefinitely. And a number of factors have finally jump-started this effort that we're here to talk to you about to define the future for inorganic carbon CRMs. I'd just like to make one point in closing my comments that the issue here is not, oh my God, NSF doesn't want to pay for this anymore. It's really just that, we collectively need a more sustainable model that doesn't rely on a single laboratory, a single individual, and a single way of going about funding this. And with that, I'm going to turn this over to Andrew.
I'm looking forward to how this turns out and the kinds of questions we get moving forward. I'm going to talk very briefly about our program for producing reference materials, which in part led to this National Academy document you can see the cover for on the right, and the idea that it could be extended more broadly than just seawater CO2. And I'm going to leave you perhaps with a couple of thoughts of my own on what you need to remember moving forwards. So I hope that many of you had an opportunity to listen to my earlier talk, which has appeared on the OAP program YouTube channel, in which I give much more elaborate information about our preparing of these reference materials, which many of you recognize probably from the picture of the bottle on the left there. So really altogether, we produce about 3 separate reference materials at Scripps. We produce one that I refer to as CO2 in seawater, which is a natural seawater that's been filtered and poisoned. We've been distributing this, as Hedy said, for 30 years, since 1990 was when we sent the first ones out, though in small quantities. In the last 5-year period where it was, so to speak, normal, we were producing over 10,000 bottles of this each year. And of the total that we sent out, probably about 1/3 was being used by scientists from the US. And this material is calibrated for total dissolved inorganic carbon, and since 1996, also for total alkalinity. So that's the first and primary reference material that we send out. Another has been this tris buffer, which is made in synthetic seawater of a nominal salinity of about 35. It's been distributed for about the last 15 years. And in those 5 years, we were sending about a little less than 500 bottles were being produced each year, of which about a half were being used by US labs. This used to originally to be calibrated using Harned cells, which is a rather tedious approach to doing it, but it's doubly tedious because it requires the synthetic seawater use purified salts that have no bromide in. And so more recently, we're actually just making it and confirming the pH using spectrophotometric measurements to show that we're getting the same sort of value as we got for previous batches. The third is an alkalinity titrant. It's a mixture of HCl and sodium chloride. It's only been distributed for about 5 years. We produce probably about 100 bottles a year over that period. They're 1 liter bottles. It's calibrated carefully by a coulometric titration. And as you see, of this, probably most of it, 4/5, is used by the US. The reason for that is probably that A, it's significantly more expensive per bottle, and B, it's additionally more expensive because the cost of shipping, being as an acid, it's considered potentially a hazardous material for shipping purposes. And so it's more cumbersome to ship and thus more expensive to ship. So here, the last 10, 11 years of the CO2 in seawater reference materials, and the blue are the amount we bottled each year. The little numbers you can see are how many separate batches we were doing. The purple are the ones that actually went out of the lab heading off by FedEx. There's probably a mismatch in part because my own lab uses some additional ones out of that, in addition to the calibration. In this point here, you'll notice that this figure for 10 doesn't quite fit with the 8 and the 9 so perfectly, because we're basically moving to a larger container so we can produce more bottles per batch. And as we go across, you see that it's steady then after that until suddenly 2020 and 2021. Where we had the COVID pandemic, which substantially put a crimp in our style of doing this. Basically, the effects were as follows. UC San Diego closed down in the middle of March in 2020, and we stayed out of the laboratory until about July of 2020. Then we started shipping again, but we were not preparing new reference materials. Our habits before that had been to have 8 people working together in a relatively confined space so as to be able to bottle about 1,250 bottles in a 1-day bottling run. That clearly was not practical. By December, we said, well, we got to produce something. So we tried a small run, which is just 200 bottles, which was 2 separate shifts, each with 1 person there, thus keeping the COVID distancing because nobody else was in the lab at the time. This year, we've increased this. We've done 6 batches so far, about 3,600 bottles. We've increased the number of participants with time, going from 2 shifts of 1 person each. The most recent batch last Friday actually did over 1,000 bottles, and it was 2 shifts each with 3 people there, because my university has now allowed us to have more people in the room. It's a room where it's easy to have plenty of fresh air because it's next to an open roll-up garage door, and this is, after all, Southern California summer. So the air is as fresh as ever, but it's at least comfortably warm. And so we got a lot done, but we also prepared a batch of tris and a batch of titrant. And we restarted in May of this year distributing. The lag was because we'd cleared out our old stocks, but we now had to prepare new materials, and we had to make sure they were stable, and we had to calibrate them. And we're currently handling a backlog of requests, which is, last time I heard, which was just about the beginning of May, we had requests for about 7,500 bottles. And we basically decided we couldn't possibly help that adequately. So we've been sending people about 40% of what had been hoped for. So if you wanted 20 bottles, not a chance, but there was a good chance you'd get 8, possibly 10. If you wanted 200 bottles, absolutely not a chance, but you'd probably get 40 or 80, about 80. And so we've been handling these requests, and they've been going out. And, you know, you saw on that previous picture that a limited number have actually been distributed this year as a result. And in fact, we're hoping to be back to normal production and distribution by next calendar year. I leave it that long because I've got to get us up to our normal bottling size, which is 1,250. And this is we've been doing it about once a month, and we probably need to keep doing that for a while. But that means we have to keep washing 1,250 bottles as well. And that's the really slow part. And the comment from Chris Sabine, who's suggesting if he wants 20, should he ask for 200? You could try it, but I wouldn't back up that for sure you would get that. We were happy to say that at the moment when we had already all the requests in hand. Thank you. So what's the immediate future of these reference materials? Well, I've been recently funded by the NSF Chemical Oceanography under Hedy until April of 2024 to continue with this preparation, calibration, and distribution. Clearly, we're currently working to clarify the overall uncertainty of our calibration approaches. As you'll recognize perhaps when you hear from Regina, the concept of uncertainty is not usually the oceanographic thing of what's the precision. Our precision is really very good, but we'd like to be certain we were right. And we have reasons to believe we ought to be, and we're just trying to nail those numbers down and write the papers. The next is to say, okay, there's an interest in calibrating these for additional parameters. We've been doing this somewhat for pH with plausible success, but we still have a problem in understanding any idea about what the uncertainty might be there. And there's an interest in doing it for carbon isotopes in the total dissolved inorganic carbon. In fact, there's a session this Thursday in this OCB meeting discussing this. And there's also an interest in using our reference materials as test samples for future studies of laboratory measurement proficiency. That, of course, is relatively straightforward to do. We have the skills to make the samples. The problem is there is only a limited amount of time and people washing bottles and getting it done in among trying to work back up to sending out about 10,000 bottles a year. And I'm still dreaming of finding a suitable alternate container instead of using a nice borosilicate reagent bottle. One that could be thrown away and didn't have to be washed again would be really nice. One that was flexible, and so you could dispense all of the sample without compromising the CO2 content. That would be great too. And one that actually you didn't need mercury chloride in to keep it poisoned would be good too. And we're still thinking about this and examining various possibilities, but it has been definitely somewhat of a sideline in among doing all the preparation. So my thoughts on the planning for the longer term is, as we think about this, and as you think about questions, think about the benefits of having the reference materials, versus the costs of having the reference materials. You need to decide what quality of reference materials are needed. To a rough approximation, the lower the uncertainty of the certified or calibrated measurement, probably the more expensive it was to do those calibrations. You also need to have the ability to keep them stable for long periods of time. It needs to be sustainable. Got to be able to keep it going despite small details like pandemics in the background, perhaps, or elderly scientists retiring, which is not out of the question. You will have noticed my hair is no longer as dark as it once might have been. Resilience of reference material production. Well, if one area shuts down completely, let's imagine an earthquake that completely damages San Diego, fine. Could somewhere else start immediately? Probably not. But we need to think about the benefits of dealing with these things, but there's costs as well. And of course, you need to think from the present points of view of the scientific community, the people that would help pay for it, the actual people that would do it, and the people that would be likely customers, and thus ultimately getting some of the benefit, but almost certainly shouldering some of the cost. So that said, I'd like to thank all the many institutions and individuals who got us to this point. This started as a project that Dave Keeling and I talked about at a SCORE CO2 meeting in the mid-80s. And we put in a proposal, and then we put in a cheaper and more carefully written proposal. And then I got funded, and as Hedy noted, we have been funded since. Scripps, of course, who've provided me with the facilities to help do this, the OAP, who are organizing us here, things, and the NSF, who we've talked about throughout as being loyal sponsors, and the Department of Energy, who paid some back in the 1990s. So, thank you. There's a note suggesting if you're going to ask questions, which will be dealt with later, use the Q&A box.
Okay. Hello, everyone. My name is Regina Easley, and I am a research chemist at the National Institute of Standards and Technology. And first, I wanted to thank Andrew for that presentation. And today I'm going to give an overview of a potential model for the US CO2 reference material node. And this is the Traceable Reference Material program that NIST has. So just to give you a brief overview of NIST, we were established in 1901 as the National Bureau of Standards. We are one of our nation's first federal labs and our nation's metrology lab. Our mission is to promote US innovation and industrial competitiveness by advancing measurement science, standards, and technology. With regards to standards, we offer a wide suite of products and services. We have over 1,200 standard reference materials in our catalog that also includes 100 sets of standard reference data and 600 types of measurement services. So just to kind of put our production into context with the presentation that Andrew just gave, every year we sell about 32,000 units of SRMs to, I think it's like 60,000 customers. And about 25% of those customers fall outside of the US. About 80% of the SRMs that we produce are in the chemical measurement space. So these range from high purity single element solutions to complex matrix standards, like ones that would support clinical measurements, environmental measurements, and industrial measurements. My focus has been on the NIST SRM program for pH standards. This program was actually started back in the 1940s with the first issue of a phosphate buffer in 1945. So we're able to make high quality and low uncertainty measurements using primary Harnett cells. And this is very similar to the system that Andrew actually has in his lab. And with this system, we're able to quantify the total uncertainty of the measurement. The one difference is the volume of units that are produced per year. So in Andrew's lab, they produce, as he said, about 10,000 units of reference materials per year. For our typical NIST SRMs, we can expect to sell between 80 to 100 units per year. The way that we issue our primary SRMs is that for each new batch of a buffer, which is sold as a salt, we actually bottle about 1,200 units. We certify that batch and we make enough so that that supply can last about 10 years. So there's a huge discrepancy in the level of production between the two spaces. The good thing is that this type of challenge is not unique. So back in the 1970s, when the Clean Air Act was passed, and during that time, the EPA was also established, there were regulations that were required, certified standards to maintain the national ambient air quality standards. The issue at the time was that commercially produced gases were too inaccurate and unstable to produce the quality of measurements that were needed. And so stakeholders, including the EPA, NIST, state agencies, and other industry partners, they met and they decided that in order to comply to the regulations that were produced, producers that were making these standards for gases should produce gases with accuracy within a 2% threshold of the values that they were certifying. The other challenge at this time was the volume of gases that were available to the end users. So with those two challenges in mind, over time, a cyclical checks and balances system was established. And a lot of this started around 1978 with the documentation of EPA protocols, which basically specify how specialty gas vendors can produce mixtures of gases that can be used to ensure the regulations. So in 1992, the NIST NTRM program was started. And then later, and I think prior to 2011, there were also audit programs that were established to help check the quality of gases that were produced by specialty gas vendors. So NIST provides their service of standard reference materials. The specialty gas vendors help in this process by producing in mass and selling those units to the end users. And I'll talk about, well, very briefly, each one of these parts, components. So for the NIST NTRM program, it was established in 1992 to help increase the supply of gas reference materials that had a low uncertainty and also NIST traceability. So for our typical gas SRM program, our gas metrology group, they decide on the standards that will be produced. They produce the cylinders in batches of about 50 cylinders, and then they measure each one to provide the certification. The difference with the NTRM program is that the specialty gas producer is the one that initiates the production. This process is coordinated and scheduled with NIST. The gas producer actually produces the cylinders using protocols established by NIST, and the manufacturers then will test all of the cylinders within that batch. The extra step is that 10% of those cylinders are actually sent to NIST for testing. And at that point, NIST reviews the data from the specialty gas manufacturer, and they do a comparison between the manufacturer's data and NIST data. And at that point, they can make a determination if the batch of gases can actually receive the certificate of traceability to NIST. So this process was able to greatly increase the amount of reference materials that had that same low level of uncertainty as the NIST SRMs. If you want to know more details about this process, there is a NIST special publication. So NIST SP 260-126. And in this special publication, it details the history of the program, and it gives information about how a producer can actually qualify to be part of this process. They have to be ISO 17025 certified. It provides information on how the batches are planned and scheduled and certified, and traceability schemes. So this is a good resource. The thing with the NTRM mixtures is that those are simple solutions. So for example, carbon monoxide in air, propane in air, or methane in nitrogen. There are cases where there is a need for a more complex mixture. So in those cases, the EPA gas calibration standards traceability protocol was established with a collaboration between the EPA, NIST, state stakeholders, and others in industry. They came up with protocols that allowed specialty gas companies to blend and analyze these more complex mixtures. And with this guide, there are details on how you can establish traceability of your mixtures, guidance on doing the uncertainty determinations. There are sample spreadsheets that are available to make it pretty straightforward for the manufacturer, and also guidance on impurity determinations. If a company participates in this program, they are actually required to go through a blind audit process. This blind audit is called the Protocol Gas Verification Program, or the PGVP. This is coordinated through NIST and EPA. And what happens is that each year, EPA hires a stack testing company to blindly procure a certain number of cylinders from each production site. The cylinders are ordered, they're shipped to that testing company, and after they are shipped, the manufacturers of the gas cylinders are notified that the audit is actually taking place. And so they refund the money essentially to the company, but they pay NIST to analyze these cylinders. So the cylinders are sent to NIST. NIST does the analysis. In this case, I'm showing a sample data set of cylinders that have carbon dioxide, nitric oxide, and silicon dioxide, or sulfur dioxide, sorry, in the mixture. So NIST will analyze them, and our results are reported to the EPA. Those results are publicly available, and we also ensure that the manufacturer's certifications are within that 2% limit of the NIST results. And so if you fall outside of those limits, then it's possible you could be delisted by the EPA. So this system in itself has multiple checks and balances that ensure that the products are tested, they're adequately traceable to NIST, and if there are more complex mixtures or additional analyses that are needed that aren't available as a NIST SRM, those are tested through this blind audit process. And I guess the question is can this model be used for oceanographic reference materials? So just to put it in perspective, our gas metrology group, given our source of funding and our amount of staff, I think in a typical year, they can certify about 500 SRM units. Using this program through coordination with the EPA and the specialty gas vendors, they're able to produce about 5,100 SRM equivalents per year. So there's like a 10-time increase in the production capability. So thank you for your time. And now I will pass this on to Shallin.
Hi, everyone. Thanks for that great talk, Regina, and to Andrew for the talk prior. So I'm going to talk to you more about some logistics. So as Libby mentioned, I used to staff the Interagency Working Group on Ocean Acidification, and we've been talking about the resilience of the reference material system for ocean carbon chemistry work since last summer. And this conversation has happened with Andrew, as well as the federal agencies that are part of the Interagency Working Group. And so what we want to do is help us get into the future in a sustainable way to support the science that's only going to grow as carbon dioxide emissions increase. So I'm going to give you a very brief talk, mostly logistics. I have this map up here just to show that the world is a big place, and that we're just going to talk today about reference materials in production inside of the US. Libby might mention this, or if we engage in this in the question and answer period, but we have been working inside the GOAN, the Global Ocean Acidification Observing Network, to talk to our international partners about the issue related to reference materials and encourage other countries and other regions to explore starting their own reference material production and distribution, which would help obviously with the resilience inside of the US as well. As Andrew mentioned, his lab operation is a lot bigger than I realized before I started engaging with him on this topic. He mentioned that it's funded by NSF grants and fees from purchases. All told, it's about a $500,000 operation. It's a production, quality control, and distribution effort with 3 full-time staff and part-time help with operations, billing, and scientific oversight. So it's a big operation. He did mention his annual output, which is 10,000 alkalinity and DIC bottles sent to 40 countries and 250 shipments, 475 bottles of the tris buffer, and 110 liters of the calibrated titrant. And so this is no small operation, and there's multiple products that his lab is producing. When we thought about options for the future as the Interagency Working Group, we wanted to consider what we saw as the entire universe. So this is an example of this kind of universe slide of options. And this includes succession planning for people, processes, and financial planning. So there you could have an option where you hope to continue operations at Scripps, as is status quo, acknowledging that succession will happen. We could also consider moving the current laboratory elsewhere, but seeing if Scripps would like to stay the host. We could try to retain the current facility, the current laboratory, but change the operating institution if that's a possibility. We could also look into retaining the current laboratory, but changing the home institution of some of the staff. And as a little note, this is what Keeling did with some of his reference work. And we could also think about just establishing a new laboratory or multiple new laboratories. But we do want to note that these laboratories can't blink on and off. They have to have a long-term commitment to producing quality CRMs over the long term. And we do acknowledge that just starting a new laboratory will require significant initial investment for space and equipment. So we are thinking on a very big scale. While it's easy to say, let's just keep on doing what we've been doing, we do know that that's not necessarily the best for resilience over the long term, which is why we're thinking bigger. Oops. So some questions that are driving our work and we're hoping to engage with you on is what kind of carbonate chemistry standards does ocean acidification work or ocean carbon science need going into the future? So what Andrew has produced has been incredible for our fields to date. Could there be some tweaks to those to better support the science into the future? And we don't want to say that just because we did something in the past, that's what we have to do in the future. We want to think about this process of change to support our scientific needs. And there are a variety of options for how we can make the US CRM enterprise sustainable, and we want to consider all of those. So Regina presented some ideas for how NIST has gotten involved with similar efforts in the past, and there's a variety of pathways we could take here, and we probably should take a variety of pathways in terms of resilience. So you'll see in the link that Heather added to the side, and we've probably gotten this over email or seen it on the information exchange, we would really ask you to contribute to our community survey to help us understand which of the Dickson products you currently use, which seawater carbon chemistry reference products you think you'll need in the future, the science you use the Dickson products to support, and if you know of any entities that may be interested in getting involved in the CRM production or distribution. So you can, like I said, check the chat box for the survey link. Heather also posted a link to the Ocean Acidification Information Exchange, which is the big picture here, and off to the right is our conversation space related to this discussion here today. So we're hoping to continue our conversation beyond today and also open it up to people who aren't attending OCB today. So these are folks throughout the US and the world who are thinking about ocean acidification and carbon, ocean carbon science. So that is my brief presentation here on logistics. And with that, I think it's time for us to take your questions. So I'll pass it over to Mike and Courtney to help with this.
Hello, everyone. My name is Mike Acquafredda, and I'm a postdoctoral researcher at the NOAA Ocean Acidification Program. I have been helping Shallin and Andrew and Libby and Hedy and Regina and Courtney CRM resilience effort, and I'm going to be moderating the questions today along with Courtney. So the first question we received is directed towards Andrew, and it is, should there be some minimum demonstrable qualifications for a potential lab to start producing reference materials? And assuming yes, who do you believe is qualified to make that assessment?
The difficulty in answering that question is there are two parts which are somewhat separable, potentially. First, you have to be able to make the reference material, produce it, and you have to have the analytical capacity to show that it is stable with time, so that in principle, it makes sense to give it to somebody else. The next part is you have to be able to assign a calibrated value to it, ideally that you know the uncertainty of, and that is a much more skillful task to achieve and requires more skilled personnel. There may be some benefit as one transitions to think about these things separately, but undoubtedly, the minimum demonstrable qualification for the lab to start producing them is that it can be shown and has been shown that they are stable materials. That's an absolute minimum. Beyond that, any value that they apply to these has to give, you have to have confidence in how appropriately and carefully the analytical chemistry is being done. And that's largely in our community been dependent on the skills of the person rather than a standardized technique of following up on quality. Regina noted the ISO 17025 documentation, which perhaps goes into this in more gory detail. And certainly a lab that is appropriately qualified that way would have made a very good start towards being able to do this. But at some level, because the community needs to adopt these and use them, it's the community's comfort level with what's going on that also counts. And so qualified to make that assessment becomes a lot more nebulous than one might wish, and I don't really have an answer.
Thank you for that answer, Andrew. To briefly introduce myself, my name is Courtney Cochran. I'm with the NOAA Ocean Acidification Program and provide staffing support to the Interagency Working Group on OA. Regina, this next question I think is one for you. What is the relationship between NIST and the specialty vendors? Does NIST have scientists embedded in those operations?
So for the NTRM program, from what I have gathered by reading about it, is that NIST does not have scientists embedded in the vendor space, but they work very closely with the vendors to plan the production of the gas mixtures. I know something that's happened over time is that just the needs of the community have changed. And so with that change in needs, NIST has also produced other types of reference materials to basically expand the catalog of NTRMs that are available. NIST also does require that there are a certain number of meetings with the personnel from the sites, and NIST will do site visits. So that's another way to check on, I guess, some of the qualifications at each site.
Thanks, Regina. So our next question isn't directed to anyone specifically, so maybe anyone could jump in if you feel fit to do so. Since reference materials are used in more than 40 countries, should other countries be engaged in helping to produce them?
So go ahead. You go first, Andrew, then I'll.
Sure. Very, very briefly, I'd like to make the following comments. As I noted, 2/3 of our seawater reference materials go to foreign countries, who also pay the costs that we charge plus the shipping to them. Were we only to prepare 1/3 of the amount of material, undoubtedly money would be saved. It would not be 2/3 of the money. So the costs being charged to US would go up accordingly. So at some level, they are already paying. Yes, encouraging other countries is a good thing. Europe has recently had a first primary experiment in trying this through the ICOS, and Japan has done it to some extent over the years as well. But the more, the merrier at some point. The key for worldwide science is presumably worldwide coordination between separate producers.
I just wanted to weigh in and say that I want to reaffirm the U.S. commitment to at least providing and maintaining the current level of quality of reference materials that we have so far been able to provide the global research community through Andrew's incredible good work and perseverance. So we're not planning to pull back from that, but we do recognize that that having multiple countries producing is just a smarter way to go in terms of being resilient, especially as seen in this pandemic. Not that, well, actually, we've all been pretty hit, so I'm not sure what country would have been less affected. But I think having multiple lines of production, but having them tracing back or cross tracing somehow, so that it isn't like we have completely separate systems, is important. And we are having those conversations through some international groups, such as the Global Ocean Acidification Observing Network. We consider that also a priority of the network. We don't have any solutions yet, and we don't necessarily have targeted countries, but I think the more we have this conversation, the likelihood that some country or maybe multiple countries come forward will happen. So I don't know if anyone else wanted to say anything about that.
I think this has been elevated at the UN Ocean Decade as well, right?
Right. I mean, to the extent that the decade actually is going to make things move forward, which is, we don't know yet. I mean, we're hopeful. It is part of the sort of OA coordinated program work that will be happening through, the UN Ocean Decade.
Thank you all for that discussion. Shallin, the next question is directed towards you. Are there requirements for CRM quality that are different for OA than from GoShip? We know that GoOn has weather quality measurements. Is it possible to have weather quality CRMs?
I can see that question is from Chris Devine, and Chris, I am thoroughly qualified to answer that question as a biologist. But as someone who used to help the IWG, I can raise that question, as you have, for the community to consider. And that's the type of thing that we're hoping the community can engage on as we go throughout this process. Dickson's standard so great for understanding the progression of ocean acidification, small changes in ocean carbon chemistry in the open ocean environment. Do you need that type of precision if you're running biological experiments like I do in the laboratory? I think Andrew has answered this question for me before, and the answer is likely no. You don't need that type of accuracy and precision to distinguish treatments in a laboratory setting. So if there was a different type of reference that would be more suitable for, say, my laboratory work, where the higher precision and higher accuracy reference materials could go to GOSHIP, maybe that would be a better system for us to support as a nation and as a community. So I'm just really excited to see that question and that type of thinking, because I think that's what we need to do. And then I'm going to just pass off to Andrew, who is the more appropriate person to answer this question.
Yeah, my own comments, again, it comes back to the two directions I mentioned. I find it hard to imagine weather quality in terms of the stability of a reference material. It's either stable or it's not stable. And sort of stable is not really a concept I'm comfortable with. When it comes to the quality of any calibration value assigned to it, clearly to achieve weather quality, one needs something that's meaningfully better than that. Does it have to be as far better as we strive? Probably not. So that is an option, that the saving, that if you can produce stable materials, it may be that calibrating it is more straightforward. My own opinion is that the key for the OA community is to better understand how their own laboratory quality control can be put into place, such as it uses access to reference materials in a limited quantity rather than in the rather extreme amounts that are typically used on GOSHIP cruises. And I think if you only use one material every so often and otherwise have internal calibrations, you probably likely do not end up with quality as good as the reference material, but you need to know separately what quality you do end up with.
All right, thank you for that discussion. The next is, again, kind of for anyone on the panel. Is there any coordination with the International Ocean Carbon Coordination Project on reference material discussion?
I'm aware that they know that these discussions are happening, that it's certainly been brought up there in the way that it has been discussed in regards to the GOAN, that people are interested, but it doesn't really look like they are in a position to say, this is what we ought to do now. I think keeping them as part of the discussion is important, and making clear why we're making decisions here in the US is equally important.
Yeah, I just want to say one more note on that. So the IOCCP is definitely represented, that Ocean Carbon Coordination Project is represented in GOAN, the Global OA Observing Network, as well. So, and on top of that, Kim Curry, who is I think even maybe a co-chair of IOCCP, is helping me through GOAN to lead this effort. So GOAN and IOCCP are very compatible and are sharing information all the time. So I'm not sure if it's been brought up in their plenaries or even how they operate, but I think there's a lot of crosswalking that is happening.
Thank you. For the next question, the academic system does not incentivize this type of work. It's almost considered service. And as such, it seems that new CRM labs don't fit at academic institutions moving forward. Do any of the panelists have thoughts on this?
My only comment would be, I can see why you might say so. I doubt it's 100% rule.
Yeah, it's an interesting thought to bring up, and something that we've discussed in the interagency working group as well. You know, when you think about longevity, quality control over time, which, you know, for Andrew's staff, many of them have been with him for, I believe, decades, right? So having some kind of stability is a good thing, which you can find in the federal service or the academic world. So, you know, potentially it's a mix. I think it's just getting the right situation, you know, the right scenario of players to come together to create a good future. And it might be multiple situations that help us in the long term.
And there is a well-known, sorry.
Go ahead. I mean, I'm going to pass it back to you, Andrew. I do feel like there's always an ongoing element of research around the reference materials, which is why, you know, Andrew has been the point person for so long. There's been a lot to figure out. Now, whether we get to the point where we just, you know, have an approach that always works is, you know, anyone's guess. You know, where we wouldn't want to be tweaking and troubleshooting it, and as Andrew said, come up with a bottle that's not the bottle that we're using now, or, you know, mercuric chloride and the organisms that are resistant to that. Like, there's a lot that is kind of behind the scenes that that makes it an academic pursuit is all I wanted to say. I don't know, Andrew, if you want to talk about.
I think you're completely correct in pointing that out. And the analogy for ocean sciences is perhaps to think about the preparation of salinity standards, which for many years was either in an academic institution, which took it for, I think, the first, you know, 60 or 70 years. And then it was in an academic government lab. And then when Britain decided that academic government labs needed to be more valuable, it was privatized to the Ocean Scientific that deal with it now. And Ocean Scientific, in order to keep being able to deal with this, have had to radically expand what they did as a commercial venture to make it manageable. So if academia and government labs throw it out, it's going to be more awkward, I suspect, to really get what the scientific community believes it needs.
So we have a little bit less than 5 minutes left. So if anyone in the audience has other questions, please feel free to put them in the questions box. We have another one here that says, will there be any effort to quantify excess alkalinity present in certified reference materials production efforts going forward in the next production and distribution model?
In the next production and distribution model, that which is yet to come, I have no idea. In this one, it's certainly a relevant research interest of my own. I think that it's likely that it will be apparent that there is such present in all our certified reference materials. Myself and my former graduate student, Michael Fong, who's supposed to join the NIST later this year, showed that it was reasonable to imagine it existing all over the oceans. So why not in the seawater we get in? How much it gets quantified and how helpful that really is to people that want to use this as an alkalinity reference material is less clear. One possible consequence is that the whole concept of measuring alkalinity is recognized as problematic and gets abandoned, and therefore there needs to be much more emphasis for pH and PCO2 than we have to date, or even carbonate ion concentration. So quite how that goes, I don't know, but in the short term, it's certainly of interest to me, and I can't imagine that it will not remain of interest for the community for a while longer.
Thanks, Andrew. Another question was, if a recommendation to expand the use of DIC reference materials to the analysis of carbon isotopes is made on Thursday, is this something that can be included in the planning process going forward?
I can't speak to the planning process. Shallin should do that. But what I should comment is, at some level, we believe that as our reference materials are stable for total carbon, and have in the past been showed to be stable for carbon-13, that if they were properly calibrated, they would be useful for isotopes. However, we use so much every year, it would be a significant effort to calibrate every batch in that way. And understanding how that is finessed to be at once helpful and efficient is part of the planning if it were to be proposed as a desirable way to move.
Just to kind of take the baton from Andrew, I don't see this as a top-down process. I see this, very much being a bottom-up process in which the community needs to tell us what they need for their science so that we can try to design a system that works to support that. So I'm really glad that you raised this question. I do hope that you filled out the survey and can put it in the comments there. If you filled out the survey and didn't put it in the comments, put another one in, maybe just with some comments, or send me an email or put it on the information exchange. This is exactly the type of information we want to see and we want to hear from the community. So please don't say that think that this is going to be, a change is going to be imposed on the community. We want the community to embrace the change and us to build it together.
I went ahead and dropped the link where we'll be continuing the conversation on the Ocean Acidification Information Exchange. Drop that link in the chat box. As Libby said at the top of the hour, if you're not already a member of the OAIE, you totally should join, and we would love to continue this conversation there. At this time, I'm only seeing a few other comments in the questions box. We have about 3
those
seconds.
questions over, right? We'll bring the questions over. So, are we off? Are we on?
I just put my email in the box.
Well, suggest live, so.
Yeah, so I put my email in the chat box. If there's anything that you want to talk about from today's session, feel free to email me directly, and I'm sure the others would welcome an email from you all as well.
Yeah, thank you so much for attending and assuming we're still on. And yeah, we really look forward to continuing the conversation. And the reason we're doing this is that we have to make these changes together as a community. It's not really going to work if we just make a decision ourselves and tell you guys to switch, because it only works because we trust each other and because we believe that, we've taken the scientifically robust path. But thank you, all the speakers. Oh, I think we're off.
You're still on, but thank you all so much for a great discussion.
Thanks, Heather.
To the venue, Heather. Thanks for coming, everyone.
Thanks, everyone.
See you all.
We're about to welcome Chris Devine to the stage. There he is. Chris needs no introduction. Chris Devine from University of Hawaii is going to share a presentation. Chris, are you sharing your own slides? Yes, you are. Fantastic. Is going to give an update here on the Integrated Ocean Carbon Research report that was just came out a couple months ago. So take it away.
All right, thank you. Hello, everyone. It's great to be here, and I'm honored to provide an update on the Integrated Ocean Carbon Research document that was, as Heather said, just published. I actually talked about this at the last OCB meeting, and at that time, we had just identified our various sponsors that are shown here on the left side of the figure. And so these are different international research programs, Ember, SOLAS, CLIVAR, et cetera, that all had ocean carbon components to their research projects over the last, say, decade or so. But all of those projects were kind of finishing up. So there was a thought that perhaps in the next phase of research, what we really need to do is to pull all these groups together and think about carbon research as a more integrated program. And so this was adopted in late 2019 as a formal IOC working group. And this has all been done kind of in the context of the United Nations IOC program. And so on the right, you'll see the cover of the document that was just published. And there's a link at the bottom. I'll show you a link at the end too. So no need to follow up on that. Let me just say a few words about what's in the document and a little bit of the motivation. This is a diagram showing the cumulative global sources and sinks of carbon between the pre-industrial and 2007. And what we see here is that the ocean really is the only other real consistent sink for anthropogenic carbon aside from the atmosphere. You know, we hear so much about the land sink and what's going on, but the terrestrial people have this way of breaking apart the sources and sinks and talking about them separately. But if you put them together and think about them as the net flux as we have in the ocean, you see that even as late as 2007, that the land was a net source of CO2 to the atmosphere. And so that tremendous sink has been offset by the sources from deforestation. So it really is critical that we understand what's happening in the ocean, and in particular, what's going to happen in the longer term moving forward. And that's why we're promoting this integrated research. This is just a kind of a figure from the report that is intended to make the point that there are lots of parts and pieces out there already existing. We acknowledge that. But the idea now is that we need to pull all these things together. So if we start in the upper right, the little eyeball icon, you know, we've got all the sustained observations that are being made consistently. We've got various process studies that have been conducted. We've got modeling efforts that are looking at prediction of what's going to happen in the future and kind of validating the limited observations that we've got in the ocean. There are people thinking about mitigation and adaptation approaches, risk, vulnerability assessments, particularly with things like ocean acidification, but climate change in general. And all of that is ultimately tied to ocean carbon uptake and storage. And then, of course, we've got the assessments. These are done at a whole range of scales from regional to global. Of course, the IPCC comes out regularly with their assessment reports. And so all these pieces need to be really connected and tied together. And kind of as I just mentioned, there are all these pieces that we've got. There are also laid on top of this all these different international and large-scale programs that are developing. So you've got the UN Oceans Decade that started this year. We've got the Sustainable Development Goals. I mentioned the IPCC makes these regular assessments, and that's feeding into you know, the regular COP meetings and how governments are thinking about addressing climate change. And none of this really can be done appropriately or properly without understanding the ocean's role in global carbon cycle and the ocean's role in the future as we move forward. So again, that's kind of the background and the impetus for why we're working on this now and where we hope to go with it. The document that was just recently published was intended to be a very high-level, broad picture view of some of the outstanding questions that are left. And we kind of broke these down into 4, again, very broad but foundational questions, and that have differing levels of understanding. So the color coding here is kind of indicating our current assessment of how well we feel we're addressing these questions. The first of which, is the assumption that the uptake of anthropogenic CO2 in the oceans is primarily an abiotic process, right? So we understand, we know that ocean biology, for example, has huge sources and sinks of CO2 from the surface ocean. But if we go with the assumption or the understanding that ocean biology is primarily nutrient limited, either macro or micronutrient limited, and not generally carbon limited, then the assumption has been that ocean biology really hasn't changed over the last 200 years and therefore does not really contribute to the uptake of anthropogenic carbon. Now, we also know, just from intuitively, that that's not really true. If we think about the impacts of ocean acidification, if we think about climate change and its effects on stratification and other processes, that can certainly affect ocean biology. So again, this is just a fundamental question that we might ask for going into the future. Another is, what's the role of biology? Again, tied into what I just said, how is it changing? What are the exchanges of carbon between the land, ocean, and ice continuum, and how are they evolving over time? And what is the role that humans are playing in all of this, particularly in the coastal zone, and particularly with the thoughts towards purposeful carbon dioxide removal from the atmosphere and storage in the ocean. So again, let me talk a little bit about these. I kind of already mentioned this first question about the abiotic processes that are going on. So this is just a diagram illustrating that we kind of see these diagrams all the time. It's very popular for IPCC assessments and so forth. This one is one we put together for the period from 2010 to 2020, that decade. But again, you see that the uptake of the ocean is estimated to be about 2.5 petagrams of carbon, and that's assumed at the moment to be an abiotic process. But we need to confirm that with sustained observations, with more modeling and analysis, more tools and platforms for making these measurements, and then of course integrating all of these results together. I'm going to talk about these other questions with respect to this general diagram as well. So as we move on to the next question, we see just this one arrow here kind of pointing to ocean biology. And so the thought has been that, from this global perspective, do we really only care about the biological uptake of inorganic carbon at the surface and then its remineralization within the ocean interior? The diagram to the left just illustrates that buried within that are a whole range of biological processes that we need to understand that all can directly impact and affect the inorganic storage of ocean carbon, and even the storage of ocean carbon in terms of dissolved organic carbon. These are all things that have been studied and are being studied but really need to be integrated perhaps into our global perspective of the uptake and storage of anthropogenic carbon. So we need to really begin to incorporate biological sampling into our inorganic carbon observing schemes and really connect those two with simultaneous measurements so that we can better connect what's happening on the biological side to what's happening on the inorganic side. The next question takes that even a step further. In the coastal zone, we not only don't understand what's fully happening on the biological perspective, but we don't even understand what's happening fully on the inorganic side. Again, in that cartoon that I showed you, we just show this one arrow kind of connecting the aquatic systems to the ocean. But in fact, there's quite a lot going on. We know that the carbon cycling in the freshwater, the rivers, is quite different from what we're seeing in the estuaries, and that's quite different from what we're seeing on the continental shelves. And not only do you have the vertical fluxes and exchanges of carbon in each of those different zones, but we also have the lateral fluxes and the movement of carbon from the rivers through the estuaries out to the open ocean that we really need to understand. And communities have been studying the estuary systems and freshwater systems for decades, but we need to promote stronger links between these different disciplines and try and work together to understand what's happening. This document also recognizes that we have a lot of the fisheries are occurring in this coastal zone. You know, a lot of the human connections, the human take of fish happens on the continental shelves or in the estuaries. And what impact is that having on all of these natural processes that are going on in this region? And that's another area that we need to understand. And that connects to this last question of how are humans altering the ocean carbon cycle? What are the resulting feedbacks? And this becomes really critical as we start to recognize that many in our society are starting to think about purposeful carbon sequestration and storage. And I remember very passionate discussions, a decade or more ago with Jorge Sarmiento and others at the OCB meetings talking about, what is the role scientific community should take in purposeful sequestration. At that time, it was really iron fertilization. And, there was kind of a general thought that, we really shouldn't get into that because our studying it would potentially promote this as a way of avoiding the reduction of CO2 from burning fossil fuels, saying, oh, well, we can just suck it up in the ocean and it won't make a difference. I think we're in a different place now, a decade or more later, where there's a recognition that we've got to do more than what's happening in our efforts to try and simply reduce CO2 emissions, reduce fossil fuel burning, that if we really want to try and save the planet, to try and make a difference, stay below that 2-degree threshold, then purposeful sequestration is almost inevitable. And if it's going to happen anyway, shouldn't it at least be informed by scientific research and studies to examine the efficacy of the various approaches and consider whether there are unintended consequences that should be considered? And you notice that we've kind of given this the red light indicating that this is an area where I think we need a great deal more understanding than we currently have. So, so what's my point in being here? Those are the four fundamental questions. These are things that obviously the OCB community has already been thinking about, and is perhaps a great model for how the international community should move forward. And I think one of the other major points that we wanted to make with this document is, as I mentioned at the beginning, there are all these different pieces and parts of the picture, of the global overall picture that have been looked at. But what we're promoting now is an integrated approach. Not just that IMBER says, oh, well, we do ocean interior stuff, so we're going to take that piece of the puzzle. And SOLAS looks at air-sea interactions, so they're going to take that piece of the puzzle. I think we've moved beyond that, dividing all of this up into its component parts, into its bits and pieces. But how can we work as a community to address all of these things simultaneously and look at the connections and the interactions between these various pieces and think of this as a whole? And so that raises a very critical first next step, I think, is, how do we manage this? What is the oversight? Our traditional approach has been to break this into these bite-sized pieces. Well, let's just look at the air-sea interactions. Let's just look at the ocean interior. Let's just look at the coastal zone. If we need to do a truly integrated approach, how might we look at this differently? We need to solidify and expand the networks of core observations. We need to develop what are the regional priorities. Perhaps instead of breaking this into pieces from a disciplinary point of view, maybe we can think about regional priorities. What are new processes and experiments that need to be conducted in this light of this integrated approach? What are new tools that can be applied? Technology is changing all the time, and we need to embrace that as a avenue for perhaps doing things that we couldn't do a decade ago. And ultimately, as I mentioned with that fourth question, consider what are the ocean's role in climate solutions and mitigation approaches. So I just throw these out as something to consider in the hopes of generating some discussion and some thought on this. I hope the remaining time that we can discuss these. And so here's that link, and I also identify the session leads, the section leads from the document, with the hope that we can continue this conversation into the future. And I'll stop there. So how do we move forward? Are we taking questions at this time, or?
Yeah, please enter your questions in the Q&A box for Chris. Keep an eye on that. Looks like there's a question from Andrew here. Do you see it, Chris?
Sure. So Andrew asks, is there an expectation that there'll ultimately be a role for more formal quality management structure to the carbon science associated with the measurement programs, such as that detailed in the ISO 9001? As has been pointed out many times, the uptake of carbon that we're currently experiencing in the ocean really only requires an air-sea difference of about 8 parts per million, or 8 microatmospheres. That's very tiny. Although these are big global questions, and the the quantities of carbon that is being exchanged between one reservoir and another is hard to imagine. It is a very small change. We are looking at very small changes in what are already very large numbers. So I don't think we can actually get away from making these high quality measurements. And because they require high quality measurements, I think ultimately we will have to continue with a formal quality management structure that not only looks at the front end of this, of making quality measurements, but also following that through in terms of the assessment products and how we maintain that quality as we begin to pull together data collected from, many different labs in many different countries. That is definitely a challenge that I think we need to address and deal with up front. So I have another question that says, from my perspective, what biological measurements are a high priority? That's a great question, and I'm going to take the same excuse that Shallin took in the last one and say, I'm a chemist, not a biologist, so perhaps there are others that are better qualified to answer this question, and I hope that we can make this more of a discussion. So I encourage you to not just add questions to this question and answer section, but also provide comments and your thoughts. I think what we need to know, really, from my perspective as a global inorganic carbon guy, is what are the net effects? The process studies and understanding the organismal or even community structure is critically important, and that's something that has been a highlight of the OCB and other groups for a long time. But ultimately, what we chemists want to know, and what the global carbon community wants to know, is what is the net effect? I think understanding how ocean biology is changing on a global scale, and how the cycling of carbon, of inorganic carbon, through the biological community is still something that I don't feel we truly understand at a global scale just yet. And so those are the kinds of questions that I'm asking, and that the non-ocean community is asking. But I ask it with a realization that there's a whole lot packed within that needs to be addressed just to answer that question. But it's a great question, and if anyone else feels that they have a perspective on this, I welcome any thoughts. So I see a question: does OCB plan to follow up on this next year? I certainly would expect that to be the case. We've tried to share the progress on this both in various international forums as well as national forums. So I think the OCB community is exactly the right community to begin to take on this task. And I would love to see a working group perhaps developed within OCB to address some of these. There is some of this. There's the Ocean Gaps working group that I believe Galen is running, that has been addressing a bit of this, but that's been kind of focused more on I think global picture and ocean atmosphere interactions. I'd love to see a similar sort of thing, looking at these addressing some of the other questions. How do you think that introducing more of the biological contribution to contribution to CO2 fluxes could change the sink source locales that we have today using mostly the abiotic approach? That's a great question, and it kind of falls in that category. I actually personally hate this statement, but it really is appropriate in many cases, where you have to ask, what we don't know, what we don't know. And again, I hate that statement, but it is so true in many places that we are very quick to take a very limited number of abiotic measurements and extrapolate that to the whole world. And it really does kind of beg the question of, where might these extrapolations really be in error, be it from biological contributions or from other, I don't know that we fully understand the river contributions or potential benthic contributions in shallow water regions, that there are, I think, many areas where we have insufficient measurements, and in particular insufficient integrated measurements where we're connecting the inorganic carbon and other measurements with the organic carbon measurements or the flux studies to fully understand what's going on. So I think there are definitely more measurements that need to be made, and that's what we're hoping to promote with this program. So I encourage you to please read through this document, work through your national or international programs that you might be connected with to raise these issues, and let's start a conversation on how we can perhaps approach this problem from a different direction, from a different perspective, and think about how we can take a more integrated approach to addressing these questions. I'd also really love to hear from the community about how they think about ocean carbon sequestration and storage. Is that something we really want to embrace and address as a community, or are we still afraid that looking into this is just going to promote more bad behavior on the part of the countries and communities that are looking for any excuse to continue burning fossil fuels? And I see that time is just about running out, but I hope that we can continue this conversation through other venues.
Thank you so much, Chris. I really appreciate you coming and sharing the details of the report. And I put a note in the chat, but yeah, that report is certainly a springboard for a future OCB activity proposal solicitation, and will likely be called out explicitly in that solicitation, as will carbon dioxide removal, ocean CDR. I think that those are two areas that are ripe for OCB action. So please be on the lookout. I put a link in the chat here for the networking directory, so you can choose where you're going to go for the next hour or so. Love to see some more faces in the networking area. There was a lot of request for this this interaction and FaceTime with people. So please use this. This is a great opportunity. Even if you want to go grab your own table and have a conversation with a colleague about a particular topic or whatever you want to do, just take advantage of it, because this is an opportunity we haven't had in a year. So I hope we can do it in person next year, but we'll see. Thank you, everyone. See you in the network.